Recording in progress.
Finding the derivatives of the inverse
An inverse of a function.
of the inverse fraction. Okay. The exercise this from problems from the book TC7.
The calculus 7.
The calculus 7 by Leetwood.
Okay. So this is from section 5.1. So exercises 25 to 40. Find the derivative of the inverse of x of the inverse of f and then apply it to x. So let's do the naive first version first. So when in mathematics, naive means has a different meaning than the normal meaning. It means you're doing it without you're doing it without uh knowledge of other methods. So this is the most basic way to do it. So first, uh, there. So now we'll just make fx into y and then isolate x so we can get it in terms of y. So now we get the derivative evaluated at y equals 1 because that's d equals 1. Boom. Okay, this is our answer. 2 over 3. Pretty easy because the function itself, f of x, is pretty easy too. So now we will need to use the more sophisticated methods for the harder functions. Suppose the f function f is continuous and monotonic on a closed interval ab containing c and let fc equals d. If the derivative of f applied at c exists and the derivative of f applied at c is not equal to 0, then the inverse of d exists and this is our theorem. So the inverse of, the derivative of the inverse of f applied at d is equal to 1 over the derivative applied at c if c is the solution. If c is the solution when f is equal to when f is applied to it and it's equal to d. So sort of c is the solution when the function is evaluated at d. So this is our theorem. Now, it might be hard to understand, so we will make an example using this problem. So let's start with making the derivative. So the derivative of square root is just the derivative of what's inside the square root. So in this case, it's 3 over 2 times the original function. So 2 times the square root of 3x plus 1. So now we will solve for c. So if 1 is equal to this square root of 3x plus 1, we will make x into c, so we can solve for it. So then 3c plus 1 is equal to 1, then c is equal to 0 because 3c plus 1 is equal to 1, then 3c is equal to 0, so c equals to 0, so just nothing. So now we will take the we will evaluate the derivative of f applied at 0, and then we'll take the reciprocal. That should be the derivative of our inverse function. The inverse function evaluated at 1, which is d. This is equal to the reciprocal of 3 over, so this is the derivative, 2 times the square root of 3. We have filled up the x here with 0, which is our c. So 3 times 0 plus 1. So that's just 1. So 3 over 2 times the square root of 1. So that's just 3 over 2. 1 over 3 over 2, which is equal to 2/3. It's the same answer, but this time it's a little, here it's harder because the function is too easy. And if we just solve for x, then it will be much easier to just do that. But for the next problems, it will be harder to do that. And moreover, it might be even downright impossible to do it without using this method. So for a of 27, function is equal to f of x is equal to x cubed plus 5. So we can still isolate x. That's the main goal here. We will isolate x for the naive method. But for some functions, it's hard or might be impossible to isolate x. So we cannot use the naive method at all, and we have to use this method, this theorem, solve it. So the derivative of this function is 3x squared. So if negative 3, which is d, is equal to f of c, so that's c cubed plus 5, we can now solve for c. So c cubed is equal to 8, negative 8. Therefore, c is equal to negative 2. So now we can substitute it into this formula. So basically now we can evaluate it at negative 3. So that's the reciprocal of the derivative of f evaluated at c is equal to negative 2. So that's just 1 over 3 for squared. So that's equal to 1 over 12. So now it's much easier. If we use the naive method, we would have to take the cube root, which is harder to differentiate. So here, we do not have to differentiate any cube roots, so it's easy. So for B. Now, here's where the naive method fails. Here, it's almost impossible. Actually, it's impossible, yes. Because this is a quintic function. Actually, is it possible? I'm not sure if it's possible, but of course, it would be very, very hard to isolate x out of this equation, especially given it's quintic. So let's say if this was a quintic and then there's a quartic term and had a square term and an x term and the constant. So that would be a full quintic. Then maybe that could be impossible to isolate x out of. So we cannot use the naive method at all. So here we have to use this theorem. So the derivative of x is 15x4 plus 6x squared. See, it's much easier to just take the derivative and get the solution and then just take the reciprocal rather than try to isolate x. Also, I'm sure that if you isolate x, there will be a lot of nasty radicals, and you don't want to take the derivative of those. It will be very, very hard. So now we can solve for c by substituting c into x, and f of x is equal to 5, which is d. So c equals to 1. Maybe if 5 was let's say like 4, maybe that'll be a good example of Fermat's last theorem. But in this case, 5 is not a perfect square, so missed opportunity. So c equals to 1. So then we can solve for the derivative of the inverse. Now we know c, we can take the reciprocal of the derivative of f evaluated at 1, which is the c we found. So that's just 15. Since x here, we will substitute that with 1. We don't mind those. So it'll just be 15 plus 6. So 1 over 21. Much easier than what if we what we would do to uh do the naive method, which we would isolate x first. So that would be first extremely hard, and then we will get the answer, which is probably a lot of radicals, or maybe uh another way to solve the quintics to maybe use like logarithms and maybe trigonometric functions. It'll be very, very hard to differentiate. So here we have like 1, 2, 3, 4 lines of 4 lines at all. So it's much easier. So first, what is the derivative of cosecant? Some people know it, but some people might not. So y is just sine x to the -1. Actually, not sine -1x. That's different. It's the inverse of sine. Here, this is the reciprocal of sine. So its derivative is -1 sine x -2, and then chain rule. We need to multiply it by cosine because cosine is the derivative of sine. So now we can simplify this. Cosine over sine is cotangent, and 1 over sine is cosecant. And there's negative, so it's negative cosecant cotangent. So we can now take the derivative of this, which is negative one half cosecant cotangent x. Then we can get c. So here, sine c is equal to 1 half, so c is equal to pi over 6. So in a 30, 60, 90 triangle, you can think of it like the short side 1, and the short side 1 over the hypotenuse, which is 2. So what is the opposite angle to that 1? So that's 30. So that's pi over 6. So f to negative the derivative, the inverse of f is equal to 1 over the derivative of f evaluated at pi over 6. So we just have to take negative 1 half pi over 6 over a times cotangent pi over 6. 1 half. So actually it's 1 over this. This is 1 over square root of 3 times we will rationalize 1 over square root of 3. That's just negative square root of 3 over 3. Nice.
Mm.
And for the last one, very simple. It's just we just have a quadratic formula to wrap this up, and then we'll get the derivative, which is 4x plus 8, and then we will solve the quadratic equation when it's equal to 1, and we get c, and then we will evaluate the derivative at c that we found, and we get the answer. So it's that simple. So that's how to get the derivative of an inverse of a function using a clearly superior method. Nice.
Nice. Thanks for watching.
Thanks for watching.